We are recording now. Do you have any questions? Yes.
What is our question, Sam?
Okay, so we just have one more topic which we're going to start talking about today, continuity, and then we have the exam. So the exam will be next week. Now, I was thinking of Monday, but Monday is a holiday. So it will be on Wednesday. Okay, so this coming Monday is a holiday. I didn't realize that last week. That's what it is. So it will be on Wednesday of next week. So ideally today we'll finish with this. If we don't, then it will extend until Wednesday. Anyways, this week we are done with everything you need for test one. Okay? So it will be next week on Wednesday. Which, by the way, I will not be here. I'm leaving to Jacksonville on Tuesday and coming back on Thursday. So somebody will be here in my instead to give you the exam. Okay? But it will be on Wednesday. Anyways, I will let you know everything next class on Wednesday.
And you're going to give us a review for the test?
Yeah, I'll be putting up a review on Blackboard. The review does not affect your grade, but it will give you a grade. You're going to see a grade there on Blackboard because I want to see how you do, and you want to see how you do when you do the review, right? But don't worry about that score. It's not going to affect your grade at all. Okay? And it doesn't mean that, okay, the review, I would say it will be maybe 80 to 90% of what you will see on the exam. There could be one or two questions that are not necessarily straight from the review. Do you understand this? So just keep that in mind. But everything we have discussed in class. If you study what we have done in class, you understand the homework, and you do a review, you should have no issues. Okay? Any other questions? Did you watch the video on Friday? Okay, did you understand the examples that we did?
Yeah, a little bit.
Did you do the homework related to that?
No, I haven't started homework. I have to do it today.
Oh, that's when you know if you really understood.
Yeah.
Okay, anyway, question comes up, then you can ask. Yes? You have a question? No? Are you okay? What's going on? I sense anxiety. Why?
Because the test.
The test is next week. Let's see, do you understand what we have done so far?
Yes.
Then there's no need to be anxious. Right? I mean, if you understand, then it's fine. It's just, the test would just be like doing the homework. Okay? That's the way you have to think about it. I'm not going to give you something that you haven't seen. You have to be, do the entire homework, etc. Yes?
I was wondering if you could give an example where you used geometry and used a unit circle to get two triangles, and then you somehow used that.
That was a proof of that special limit. The sine of x over x as x approaches 0 is equal to 1.
Oh, that's just the proof.
Yeah, I said that, look, I'm not going to, when I was explaining that, after that I said, I don't require you to know this. It's just for you to believe that statement, right? What you need to know is that when you see this limit, let's see. So, what you need to know is that when you see this limit, sine of x over x as x approaches 0, that equals to 1. So you need to know. Okay? And of course, all the variations of this, like, we did it here, where the examples. Like this is like one case, right? Like if you have sine of 2x over sine of 3x, then you can actually, not like this, but you can play with this in such a way that then you can use that property, okay? And the point is that you can split these as two fractions, and then here I just need a 2x. Remember, the whole point is that whenever you have that limit, the way to think about this is that as long as what you have here in the argument of the sign is exactly the same as what you have in the denominator, okay? And that quantity is approaching 0, then the limit will always be 1, okay? So if instead of an x you have a 2x, if I manage to have a 2x down here, and x approaches 0, that means 2x also approaches 0, right? That limit is still 1, okay? And that's all the thing that we're doing here. So I have sine of 2x, I want a 2x down here, so I put it, because I don't have it, then I have to multiply on top, right? It's over here. Why did I put the x here? because I have another guy that I want to deal with. I have the sine of 3x, I need a 3x up here. Yes, it has to match the argument. I already have the x compensating this one, so that's why I put it here. I don't have the 3, so I put it here, but if I put it on top, you have to put it in the bottom. Because it was not there. Multiply with divide. Yes? Now, when you take the limit, this is 1, so the answer is 2 over 3. And notice that you can play this game every single time. That's why we close the discussion by saying if you have a limit like this, then the answer is just A or B, whatever these numbers are. Because you can always do the same thing. Right? The 2 and the 3 were not important here. It could have been whatever. Yes? And, you know, if you have something like this, there's a 4x here. You cannot use the property immediately because that means that we only have an x down here in the denominator. What are we missing? We're missing 4. We want to make sure that what's in here in the argument is also down here in the denominator. Okay? So what do we do? Okay, I need a 4 here. Put it. But if you put a 4, what do you need to do? You have to multiply by 4 on top because it was not there. Right? Multiply top and bottom. This part now becomes 1, and that's 4. So the answer is 4. And just plot this at the beginning with numerical approximations, right? When you were doing the table and doing numerically, then you came out to the conclusion that the answer will be whatever number comes in front of the x. Well, now you see y. Okay? So all of that geometry thing that I did was to actually, that's a very important limit, and was to actually, you know, justify that so you actually believe it. Okay? And it's a non-trivial application of the squeeze theorem. Because the usual one that you might think about, which is saying, oh, sine is between -1 and 1, now divide by x, it doesn't work. Because when you apply the limit as x approaches 0 from the right, the left one goes to negative infinity, and the other one goes to positive infinity. Different values, so the squeeze theorem doesn't do anything, right? The squeeze theorem says that these two points, they have to go to the same place. If that's the same limit, the one in the middle is forced to have the same limit as well. Just think about it. Yeah, if you are here, somebody's here, and there's one in the middle, and the outside people are walking like this towards this point, what do you think is going to happen to the one in the middle? It's forced, even if he doesn't want to go there, it has to go, right? It has no choice. So that's, you know. So the point is, okay, can we still use squeeze theorem? Yes, we can, but you have to be a little bit more clear. Okay, we need to come up with another inequality that works for us, and we came out with you know, this inequality. This is actually surprisingly fact. Surprising fact that x is actually between sine of x and tan of x. How do you believe this? I mean, if I tell you that, you may ask, why? Where did you get this from? Well, geometry. Do you understand the geometric construction? It's pretty simple. You have your triangle and you have your unit circle, right? Then this is your angle x. Just turn this side to this point in such a way that when you drop down, you get a tangent here. You get a 90 degree. You can always do this. Does that make sense? All right. So, and then just draw this little line here connecting the point in the unit circle and the point 1, 0. By doing this, there are 3 geometric shapes here. This is a small triangle. There is this circular, circular sector, right? Like this slice of pizza. You see it? And then there's a big triangle. And notice that one is inside the next one, right? And next the picture. The small triangle is inside the sector, and the sector is inside the big triangle. What does that mean? If you look at the areas, what can you say about the area of a small triangle? It's less than the sector, and the sector is less than the big triangle. When we look at area. Yes? That's this. So this is what geometry is giving us. Now let's go ahead and let's try to compute what these areas are. And you know, it turns out that this point here is actually a very nice thing. Notice that the coordinates of this point is 1, tangent. This right here is equal to tangent of the angle. Because what's tangent? Opposite over adjacent. This is a right triangle. Yes? Adjacent is just 1, so the y value here is the opposite that equals tangent. And by the way, you may actually, when I was writing this, it came to my mind that actually that's probably the reason why this function is called tangent. Because notice that given an angle, this side right here, what's this side with respect to a circle? It's actually the tangent to the circle. So given an angle, to play this construction, and the side that's tangent to a circle, the length of that one is actually what we call tangent of x. That could be a reason why it is called tangent. I'm saying cool because nobody has told me this and I haven't read it. So, but I mean, it makes sense. Why would it be called tangent and not something else? At least this line is tangent to a circle here. Okay, so it's kind of. Anyways, this point is one common tangent, and that's it. That's all we need. It's x and this is 1. Now you need to remember some stuff from 3. There is an alternative way of finding the area of a triangle. Okay, and I wrote that down here. The usual way is base times height divided by 2, right? But if you have a triangle in which you know 2 sides and the angle in between, you can also find the area, which is the product of the sides times the sine of the angle divided by 2. Okay, this is the formula that you learned back in 3. So we're going to use that one to find the area of the small triangle, because we know 2 sides and the angle in the middle. And then for the sector, once again, in 3, you saw this, the area of a circular sector is 1/2 the angle times the radius squared. In our case, our radius is 1, so it's just 1/2 the angle. The angle has to be in radians for this. Okay. And for the big triangle, that's a right triangle, the area, you can look at one of the legs of being the base, and the other one is the height. So it's just the product of the legs divided by 2, base times height divided by 2. Okay? So that's what you see here. Small triangle, the area of the sector, and the area of the big triangle. And what justifies this? The geometric construction that we did. Okay? Now we just play with this, get rid of all these 2's, then we get this nice inequality, and then we start getting what we need. Remember, we're looking for sine of x over x. So I want that one to show up in the middle. That's why I divide by sine, because I want the sine in here. So, and then we obtain what we wanted. We actually computed here x over sine, but as I mentioned here, that's okay. So it turns out that x over sine is the one that is equal to 1. So we ultimately found that x over sine is between 1 and 1 over cosine. So these are my 2 functions. And when you take the limit as x approaches 0, this certainly goes to 1, it's a constant. And this one also goes to 1, because cosine of 0 is 1, right? So the one in the middle has to be 1. But remember, we wanted sine over x, but we can fix that really quickly, because sine of x over x is the same thing as 1 over x over sine, right? You take the limit, this limit of the top is certainly 1, the bottom is also 1, we just prove it. So this limit is 1 as well. Okay? But again, I'm not going to be asking you to prove these, none of that sort. This is just so that you believe this. And so you see that squeeze theorem can be used in non-trivial ways. Okay? But from this discussion, you just need to know statements 1, 2, and 3. That's what you need to know. You see this limit, you need to know that's 1. This one you need to know is 0. And you need to know that this is the definition of E. Did you understand the change of variables that I did here? Because that's a good technique also to compute limits, changing variables. Did you understand this? Yes? For example, let me give you an alternative way of solving this one. Number 2, let's solve that alternatively using change of variables. Note. I'm going to do the same one. But could do another one if you wanted to. But let me just do the same one so you see another way of doing that. So what do I mean by change of variable? Well, here's what I'm going to do. I have a 4x. Instead of 4x, I wanted to have an x in there. So I could say the limit is 1 and then be done with it. Because I done, then we need to do something. Let's just make it look like sine of something over that something. And in this case, I'm going to use a change of variable. So I'm going to let t be 4x. So this right here, let's call it t. So far, this is going to look like this. Sine of t over something. Can you tell me what is that something? If t is 4x, what is x?
T over 4.
So from here it follows that x is t over 4. Yes? So I'm changing my variables. Every place that you see an x, we need to now write it in terms of t. That's what I'm doing. Okay? So now I can write that x as t over 4. Yes? Now all we need to do is modify the limit, because here x approaches 0. Now I would like to say something about t. So the question is, when x approaches 0, what do we know about t? So what's the limit as x approaches 0 of t? What is this? Well, this is easy. What is t? T is 4x. And what's the limit of this? 0. So when x approaches 0, t also approaches 0. You understand this? Now, why it is more comfortable? Well, because now, as you know, this 4 is in the bottom, so we can bring it to a top multiplying, right? So this is just sine of t over t times 4. And now you have, the actual limit that we were looking at originally, the sine of something over that something as that approaches 0, we know that's 1. So the point is that there is this substitution idea that you can use to simplify your limit, and it will help you solve the problem. We're going to come back and look at substitution at the end. When we talk about integration, there will be a technique called integration by substitution, where you're going to be using it non-stop. Okay, in Calc 2, that will be your bread and butter. Okay, you'll be doing substitution left and right, so you need to be comfortable with that. That's why I'm introducing you to this idea here. And the point is that when you replace a variable by something else, you have to change everything. You cannot have a mixture. So I'm just relabeling 4x as t, but now everything else has to be changed. So instead of x, that's now called t over 4. And we need to analyze what to do with this. When x approaches 0, what can we say about t? Because that's my variable now. And because t is 4x, if this x goes to 0, t also goes to 0. Right? If this would have been x approaches infinity, what would t approach to? Infinity as well, right? Because 4 times infinity is also infinity. So it's just a change of variable. Same limit, it's just different variable. But now this one is easy to compute. But we don't have to play that game of multiplying by 4 top and bottom. Here, the times 4 came out naturally after doing the substitution. Okay? That's just an alternative. Okay. Are you okay? All right. So let's begin with today's topic, which is continuity. Okay. So you kind of already hopefully have heard at least about this word when you were back in pre-calc. So we want to make sense of this notion of continuity of a continuous function. The way we're going to do this is first we're going to define what it means for a function to be continuous at a point. And then once you know that, then we're going to define what it means to be continuous over an interval. Okay? Let's see, does anybody has an idea of what continuity is? Yes?
Like there's no holes, gaps, sharp turns.
Okay. Well, what's wrong with sharp turns?
It's not smooth.
Okay, that's not what we're talking about. We're talking about continuity. But that's a good point. We're going to see that continuity and smoothness are different things. In fact, if a function is smooth, it has to be continuous, but not the other way around. The function could be continuous without being smooth. Think about the absolute value function. As a sharp turn right at the origin. That point is not smooth right there. But we'll get there in the next chapter. Okay, but what would be a nicer, a very simple thing of how can you summarize all that? It doesn't have a hole, it doesn't have a gap.
Just in time.
Oh, just walk in. It doesn't have a hole, a gap. So how can you summarize that nicely? How does the graph look like? If it doesn't have a hole, a gap, nothing.
Solid line.
A solid line, good. In other words, okay, it's a solid curve, right? It has to be a line. It means that you can draw it without lifting your pencil, right? Being continuous means that you can start drawing your picture and you don't have to lift your pencil to do a hole or, then jump here and do a gap and that kind of stuff, okay? That's a basic idea. Now we're going to try to formalize that more mathematically, okay? So, but do not forget the intuition. So intuition, so the intuition is a function is continuous. I mean, that's the reason why we choose the word continuous. Like you can draw it without stopping, right? Function is continuous if we can draw this graph without lifting the pencil. Now you understand that the word pencil here is really just something classical. Nowadays, and not everybody uses a pencil, right? You use a pen. an electronic, whatever. Anyways, whatever writing device you're using. Okay. So that's what we mean by continuity. You can draw the graph without lifting the pencil. But the point is that most of the time you don't even know how a function looks like. Okay. So how do you know if you can lift the pencil or not? So let's try to put this into mathematical terms. So before I define to you what continuity is, let's actually write down examples of what we consider not to be continuous. Okay. Let's look at what we don't want, and then our definition will be, okay, we want to have those problems. We want to make sure that they are solved. Okay. So do you see what I mean in a second? I'm just going to give you some examples of instances in which the function is not continuous because they violate this property that you cannot lift your pencil. Okay, and from there we're going to formalize. So the first thing is that we're going to analyze is continuity at a point. So what does it mean for the function to be continuous at one point? And let me give you examples where continuity fails. At the point x equals a. All right, so let me draw here something. So let's say that we have some function, whatever, and there is a little hole in the graph of the function. So this is your function y equal f of x. Now, please understand that you could argue that you can draw this without lifting your pencil. Because, right, you can start drawing and then you can go around and then continue drawing. But understand that when I have a hole, it means technically that you're drawing somehow, you need to jump that little hole, okay? So it's not okay to go around in a circle. That's what I want to say. Okay, so this is, certainly we wouldn't call this function continuous at a, okay? Because the idea is that a continuous function should be very nice. Think about polynomials. They are continuous functions. Okay? These are the nicest functions around, polynomials. Okay? All right, so that's an issue that we need to address. Another issue is something that we wouldn't call continuous, be something like this. Let's say that we have this, then a function here. Okay, and this is our function f of x. Again, we wouldn't call this continuous because there is a gap here. By the way, notice that the issue that we had in number 1, it was at least solved in number 2, right? What's the problem here in number 1? What's the issue that this function has? The hole. What does the hole mean when it comes to the function? In other words, the function is not defined at a, right? You cannot find an output. That's the problem here. Now, that problem was fixed here, right? Because is this function defined at a? Yes. If you plug in a, you get whatever this y value is over here. You understand this? And now we have another issue. What's the issue? There is a gap. Okay, we want to avoid that. So we want to avoid this. We want to avoid this as well. Okay. Now, the question is, if we avoid those two, would that be enough? If we avoid those two, would that be enough? Well, how about this? Oh, draw that. So again, here we solve the first issue. The function, is defined at a. We solve the second issue in the sense that the function is not split into two whole pieces, right? There's no big gap. But still, there is a tiny little gap here, right? You still need to leave your pencil because there is this dot that you need to draw when you're sketching the graph. So it's not good. Even though this one takes care of the problem number 1 and the problem number 2, which now we're going to formalize them mathematically, okay? But you will see it actually takes care of those two problems. It still has an issue. So we want to make sure that none of these three things happen. And there's one more that I should show here, which is the function can be nice, but it may come in pieces, and therefore, as a whole, it's not going to be continuous. And that's typically when you have like asymptotes and so on. So let's say that we have here an asymptote, and then your function is doing this. It doesn't matter if it goes both ways or it could be going down one of the pieces. The point is that there are two pieces here. Each piece certainly looks continuous, but you have to certainly leave your pencil to go from one piece to the next one. This happens when you have a vertical asymptote. You okay with this? So we don't want none of these things to happen. If any of this happens, then of course our function is not continuous. Okay, let us try to characterize what's going on. So in number one, what was the problem? The function is not defined. So here, the issue that we encountered is that f of a does not exist or is not defined. Yes? The function is not defined. So if we want our function to be continuous at a point, we better make sure that the function is defined at that point. Yes? That will be our first condition in the definition. Because if it's not defined, we got a hole. That's a problem. Okay? Next one. Now here the function is defined, so that's not an issue now. What's happening here? And how can we see that mathematically?
It's a piecewise function.
Okay, but there are piecewise functions that don't have gap. Like the absolute value function is piecewise, and it has no gap, right? Because the second piece connects right where the first one stops. So saying piecewise is not enough because there may not be any gap. How can you describe this case, this situation mathematically?
The limit at a is different on both sides.
Very good. You have to look at side limits. You see, I know that there is a gap. Well, because the left limit is different than the right limit, right? The left limit is equal to whatever this number is on top, and the right limit is equal to this number in the bottom. So at the point A, that tells you that you have a gap because both sides the function is going to different places. That's how you know that there is a gap. You understand this? So in this case, in other words, the limit does not exist, right? But to justify the gap is because the side limits exist, but they are different. I'm saying this because notice that in this last case, also the limit does not exist, but it's a different type of limit. What limit do we have here? As you approach A, what's the limit? Infinity. Okay? So it's a different situation as this one. There's no gap here because the side limits do not exist. They are a type of infinity. Okay? All right. So in the second case, put this down. Make it symmetric. So in the second case, the issue that we are seeing is that, well, the limit as x approaches a per se of the function does not exist, right? But let us also say that the reason why we have a gap is because actually side limits are different, right? So let's say here, since the left limit is not the same as the right limit. Okay? That's why we have a gap. We okay? So that means if we want a function to be continuous at a point, what do we need to require? It has to be defined at the point. Second, what else do we need to require? The limit has to exist. The limit doesn't exist, you are either in this or in the situation in the bottom, right? And that's a problem. So the limit as x approaches a from both sides, it has to exist. And of course, that means that the side limit must match. But again, condition 1 and condition 2, they are satisfied by this third picture. Yes or no? Is the function defined?
No.
What do you mean no? What do you think this little dot is doing for us? Right, it's saying when x is a, the value of the function is whatever the y value is, right? So the function is defined. Does the limit exist? Yes, from both sides, what will be the limit? Whatever y value the whole has, right? Do you understand this? I mean, at A we don't care, but when you get close to A from either side, the function is going towards whatever y value corresponds to this hole. Yes? So the limit exists. So it's defined, the limit exists, but still this is not continuous. So that means those two properties are not enough. What do we need to do to fix it? You know, okay, let's first describe the issue here. So what's the issue here? The issue here is that the limit as x approaches a of the function is not the same as the value of the function, right? So you can make sense of the left or the right hand side here because you can find the value. You can make sense of the left hand side, you can find the limit. But the problem here is that they're not the same. Right? So how can we fix the situation?
The limit and the y value of a have to be the same.
You just make them equal to each other, right? Just make sure that they're the same, and then that means this dot down here actually will be here filling in the hole, and you're good to go. You have your continuum. Do you understand this? So 3 properties that you need to have to be able to make a function continuous. What are they? It has to be defined at the point. The limit has to exist. Moreover, the value of that limit has to match the value of the function at the point. Okay? If you forget that, just think about these little pictures, and they will tell you what are the things that you need to have to ensure continuity. And remember, this last one is just a case like number 2, but a little bit different because the limit does not exist, but because it goes to infinity, or the side limits are infinity. So let me say here. So in this last one, again, what's going on is that the limit does not exist. Since, I mean, in this case, you could say it does not exist, but you can also say, oh, it's infinity. But remember, in the right piece, I would have drawn it going down here to negative infinity, then the limit at a would not exist. And you cannot say anything else because the behavior is different. Okay? So, but I will say that it does not exist, and we say at least one of the side limits is infinity. Okay? So we say since at least one of the side limits, in this case it's both, but at least one of the side limits is infinity. Now I want you to understand that this is continuity at a point, okay? So these are examples of which continuity is lost at that point x equal a, okay? So let me write down the definition, and then we're gonna come back here. So we actually call these cases, we call them discontinuities of a function, okay? Let's actually talk about this. Yes, so they're called discontinuities. Now, some of these discontinuities are not too bad. Others are very bad. What do we mean by that? Some of these discontinuities can be fixed. Others cannot. Those that can be fixed are called removable discontinuities. So like the name suggests, you can remove them. Okay, you can get rid of those. Those that cannot be fixed are called non-removable discontinuities. Okay, so let's see. Let's look at these pictures. Which one do you think? Let's see. Number 1. Do you think we can fix number 1? And okay, let me say what I mean by fixing. Here is a rule. You are allowed to change the function at only one point. You can only change the value of the function at one point. You cannot change the function at an entire piece. Like for example, here you cannot say, oh, just take this right part and push it up and make it match here, because you are changing the value of the function for infinitely many x's. You understand what I'm saying? You are allowed to play with whatever the function, with the value of the function at one point. You can do whatever you want at one point. But that's what you can do to fix. Because if you change the whole thing, then you're technically changing the whole function now. Okay? But just changing one little value, I mean, it's not the same function, but it's not too bad. So let's see. Looking at that rule, can we fix the first picture? How? You see, graphically, how can we fix it? Just go and fill in the hole. Right? You fill in the hole and then you're done. What does that mean? Because the limit exists here, right? In this case, notice that the limit exists. What do? Just make the value of the function equal to whatever the limit is. You're good to go. So that will be a piecewise function, right? So it will be whatever the formula is when x is different than a, and at x equal a, you make it equal to whatever the limit is. So we'll do examples in which we do that. So it's easy to fix. So this is an example of a removable discontinuity. So let me just write it here. So we call these a removable discontinuity. Let me say f of a does not exist. And the second point is that the limit exists, okay? The limit exists. When this happens, this is called a removable discontinuity. Are we okay with this? In the second example, can we fix this by just changing the value of the function at one point? So in here, you can play with a whatever you want, but still, the fact that we have a gap is going to remain. The only way to fix is to actually bring half of the graph and either bring it up or this half bring it down. But again, now you're violating the rule. Now you're changing, you have a super different function now. Do you understand this? So this is a non-removable discontinuity. So this is an example of a non-removable discontinuity. Okay? All right? Let's look at number 3. And it's because we have a gap. Oh, in this particular case, we also give it another name. So it's non-removable, but we give it a name because this one is also non-removable, the last one. And I fix this easily. But they're both non-removable, but this one is called a jump discontinuity. Why? Because there's a gap, so you're jumping. Imagine that you are walking on the graph. When you are here, what do you need to do to go to the next piece? Jump. You have to jump. Okay? There's a jump discontinuity. And this one is called an infinite discontinuity because the limit is infinite. Okay? I'm telling you this because you're going to see all of these names in the homework. So you need to be able to understand what are we talking about. Okay? So in this case, this is called jump discontinuity. But understand that that means non-removable. Discontinuity. Okay. How about this one? And we fix this?
Yeah.
How?
Use the dot to the middle.
Very good. Just redefine the function by saying, hey, this dot should go here, not down. Right? Just change the value instead of being whatever this y down here is to whatever the limit is. Because in this case, the limit exists, right? And the function is defined. You just have to redefine it at that point. Before it was not defined, we just define it to whatever we want. Here it is defined, but it's defined to the wrong value, so just fix it. Okay? Just change the value at that point. So this is also removable. Okay? It's removable. And then the last one, as I mentioned, is also non-removable, but in this case, we call this discontinuity an infinite discontinuity because the limit is infinite. So this one is non-removable. And it's called an infinite discontinuity. Are we okay with this? All right, so then let's go ahead and let's write down the definition. So what does it mean for a function to be continuous at a point? 3 things. It has to be defined. The limit has to exist, and the value of the limit has to match the value of the function. Okay? So in a sense, condition number 3 will enclose the other 2, because for the equality, I'm not writing equality here. For the equality to make sense, this has to make sense, so the function has to be defined. This has to make sense, so the limit has to exist. Okay? But when you analyze a function, you should go to those 3 steps, because why are you going to worry about the limit if the function is not even defined? So you stop right there. Okay? So just look at those 3 steps. Okay, so definition. This is the definition of continuity at a point x equals. So a function y equal f of x is said to be continuous at x equal a if the following three conditions are satisfied. Okay, so number one, the value of the function exists. So f of a is defined. As we know, that's not enough. So number two, we need to avoid that infinity or that gap. So the limit as x approaches a of the function must exist. Once again, that's not enough. Number three, the value of the limit has to be the same as the value of the function. That's what it means for a function to be continuous at a point. Do you understand this? Okay, good. So, question. Because a typical problem would be, I give you a function, then I ask you where to figure out the points, if any, of which the function is not continuous, right? But then we want you to classify the discontinuity. In other words, once you tell me, oh, this function is not continuous at 3, okay, what type of discontinuity do we have there? Is it a removable discontinuity or a non-removable discontinuity? Okay, so let's try to see if we have a tool to be able to quickly identify that, because here we're relying on the picture. Okay, so can you tell me analytically or algebraically, how can we figure out whether a function, if it's already discontinuous at a given point, how can we figure out the type? What do you think would tell you that? So being discontinuous at a point means that one of these three will fail, right? Because if these three conditions are a check mark, then that means it's continuous. So if it's not continuous, that means that at least one of these guys is not true. Either number one, number two, or number three. Question, which one here is the one that encodes the type of discontinuity? What can you say that will tell you the type of discontinuity? For example, let's look at the removable cases. What do these two cases have in common? Removable cases were number one and number three, the pictures. Yes?
Yeah.
What do they have in common?
They both have limits.
The limit exists for both of those. Do you see that? Let's look at number two and number four. They both are non-removable. Yes? What do they have in common? The limit does not exist. So that's your clue. Okay? If you know already that a function is not continuous at a given point, and then you want to figure out what type of discontinuity you have, the answer is in whether number two is satisfied or not. If the function is discontinuous because maybe one or three were not good, but number two is okay, so if the limit exists, then the discontinuity is removable. Because you can fix it, just change the value of the function to whatever the limit is, and you're good. Okay? Now, if it turns out that the one that actually fails is number two, that the limit does not exist, then there's no hope. So you have a non-removable discontinuity. Okay? So this guy is the one that tells you the type of discontinuity, if there is any. So let me write that down. So, remark slash, and then this is how we formally define the type of discontinuity. So, if a function, if y equal f of x is not continuous at x equal a, so I'm saying that it's not continuous, okay? So that means at least one of those three conditions are not satisfied. So if a function is not continuous at a, but the limit exists, in other words, condition number two is true, we call this a removable discontinuity. If y equal f of x is not continuous at x equals a, but limit as x approaches a of the function exists, in other words, either one or three were the problem, okay? Then we call this a removable discontinuity. Okay, we call this a removable discontinuity. Otherwise, do you know what I mean by otherwise? What do I mean by that?
That doesn't work.
What is that?
Non-removable.
I say otherwise, it means
Number 2 is not satisfied.
if the limit does not exist. Is that clear to everybody, or should I write? This is just so I don't need to write if the limit does not exist. Okay? Because idea is based on the fact that the limit exists. If I say otherwise, I'm implying the opposite of this. In other words, the limit does not exist. Yes? I just want to make sure that when you read these later, you understand what you're reading. Okay? So otherwise, we call it non-removable discontinuity. Okay? So, in other words, the secret is in condition number 2. That's the one that tells you, if it's not continuous, this is the one that will tell you what type. Okay? It depends on the existence of that limit. All right. Questions? Do you understand the definition? We're going to do examples now, but do you understand what's written here? Okay, so let's do this. Okay, so this is continuity at a point. Let me just say, because it's very easy, how do we define a function to be continuous on an open interval? Because closed interval, we need to write a couple more details. But then we say that a function is continuous on an interval, on an open interval, if it is continuous at every point inside that interval. We know what it means to be continuous at a point now, so it has to be continuous at every single point inside that interval. So, definition, a function y equal f of x is continuous. Okay, from now on, I'm gonna write CONT, okay, for continuous. So it's continuous on an interval, on an open interval. So open means with parentheses, that you don't include the endpoints, okay? So it's continuous on an open interval AB if it is continuous at every point inside that interval. If it is continuous at every point inside this interval. Okay, I'm gonna talk about closed interval later, but basically you should imagine what that is. So if we now include the endpoints in our interval, we make it closed, then to be continuous would mean that's continuous on the open, so it has to be continuous everywhere inside, but then at A, we don't really care about what happens to the left because we have a closed interval. I'm only looking at the function from A to B. I don't care what happens to the left of A or to the right of B. So we have a notion of left continuity and right continuity. So we only need the function to be left continuous at A and right continuous at A and left continuous at B. And how do we define left and right continuity? Well, the usual way. The only thing is that here we will have either a left or a right limit, depending which one is the one that we're looking at. Okay? But I'm going to write that down later. Let's just do some examples. We haven't done examples, and I want to make these things very concrete. Because at the end of the day, it's very simple. Okay? As you're about to see, most of the time, a continuity question boils down to a domain question. It's just a college algebra question. I give you a function, find the domain. Because whatever the function is defined, typically the limit will exist and it will be equal to the value. Okay? Unless you have a piecewise function and then things could be changed. No? Could be weird. Notice that in all these weird cases, our functions are piecewise. Yes? But if you have a full formula, the point is that you're about to see that pretty soon is that whatever the domain of that full formula is, that's what your function is continuous. So a continuity question is just a domain question. Okay? All right. So discuss the continuity of the function. And this is a very open-ended question. When I say this, it means I want you to tell me everything that you can about the function. So I want you to tell me everything about continuity, of course. In particular, where is continuous, where is not continuous, and if there are points of discontinuity, you need to tell me the type. I want to know all of that. Okay? All right, so let's do 1 over x. Then let's do x squared minus 1 over x minus 1. Let's use all the letters F, G, H. Do x plus 1. That's now greater than 0. E to the x greater than 0. And I guess let's also do sine x. Just to have some free. Okay, so here we have some functions that we want to discuss the continuity of this function. What I mean is, I want you to tell me everything about the function. Okay, what is continuous, what is not continuous, and so on. And we typically answer in terms of intervals. If you want to say where a function is continuous, usually the problem is just, if there is any problem, it's just at some points. Okay, everywhere else there is no issue, so we answer that with an interval. Okay, the solution. So for number 1, the function f of x equals 1 over x. Remember, continuity, the function has to be defined at the point. So the first thing that you need to ask yourself is, where is this function defined, right? If there are points at which the function is not defined, those are already, you know the function is not continuous at those points. So it has to be in your list of discontinuities. You understand this? So step number 1 is find the domain. Because the domain is really what tells you where is the function defined, where is not defined. Yes? So to answer this question, we naturally have to ask for the domain. What's the domain? What do you mean by x equals 0? So the domain is everything except 0. So x equals 0 is the problem, right? So the domain is all real numbers except 0. So all real numbers x, such that x is different than 0. Another way of writing this is from negative infinity to 0, union 0 to infinity, right? That's the interval notation. Just, it's everything except 0. Are we okay with this? Everybody understand? Okay. So now, this immediately tells us, so from here it follows that, therefore, f is not continuous at x equals 0. So we found one, okay? That means that at any other point on the domain of, at any other point, any other real number, the function is defined, right? The only issue was 0. Now, the question that we need to say is, at any other point, what can we say about the limit of the function? Let's say that you take the limit as x approaches 7. Will that limit exist?
Yes.
What will it be? 1 over 7, right? 15. Would that limit exist? What will it be? Negative a million. Would that exist? What will it be? Negative 1 over a million. In other words, you know, other than 0, at any other point, the limit is going to exist, and moreover, it will just be the value of the function. Do you understand this? The only issue here is 0. So this function is continuous everywhere else. It's continuous on its domain. Yes? So f is not continuous at x equals 0, and we just say here clearly, if x is different than 0, then, you know, okay, so let me say, if a is different than 0, then the limit as x approaches a of 1 over x exists and equals 1 over a, which is the value of the function at a. Yes? In other words, at any point other than 0, conditions 2 and 3 are going to work. The function is defined, and condition 2 and 3 work, so that means the function is continuous. So f is continuous on the interval negative infinity to 0, and also from 0 to infinity. So we typically write it as a unit. Okay. So this is where it's continuous. We know then that it's not continuous at 0, the only thing that remains is to classify that discontinuity, right? What discontinuity do we have? How do we answer this question? We need to investigate the limit, right? What happens to the limit as x approaches 0 of f of x? Well, this is 1 over x, so it will be 1 over 0, but then you need to know what type of 0 is this. Is this 0 with negative numbers, or is it 0 with positive numbers, right? Are you getting close to 0 with negative or with positive? Because that will give you, it will tell you what type of infinity you have, yes? So here, to analyze this, we should look at a side limit, whichever you want. I'm just looking at the right limit, okay? The point is that in this case, we get positive infinity. In particular, this is telling us that the limit does not exist, right? The actual limit does not exist. So what type of discontinuity do we have? Non-removable. Notice that I'm not relying on the graph at all. I mean, we know the graph. You could have just drawn the graph and then it would have been way easier. But what if you have a function that you have no idea how it looks? Well, that's what you do. Just analyze it. That's what calculus does for us. It lets us understand the function without having to look at the picture. I mean, the point is to be able to draw the picture later by doing calculus on it first. Okay, that's the option. So the limit does not exist, and so x equals 0 is a non-removable discontinuity. Do you understand this? So that's everything we can say about continuity. It's continuous everywhere except at 0. And at 0, the problem is not removed. Okay? All right. And if you wanted to say something more, you can say the problem is because we have an infinite discontinuity, because one of the side limits was infinite. Okay? So I will say here infinite discontinuity. Yes?
So wait, so f of x equals 1 over x is continuous, but x equals 0 is non-continuous.
It's continuous everywhere except at 0.
Okay.
You see, x equals 0 is a non-removable discontinuity.
So anytime I get a question, then I would have to define the exact part that is non-continuous.
Yeah, the whole point is I want to know where the problem is. It's either continuous everywhere, or it's continuous almost everywhere except at 1 or 2 points. You have to figure out those points and then tell me what's going on there. Is it removable or is it not removable? And the secret is, this is just domain. How did we come up with the 0? This came up from the domain of the function. This was the issue, right? So for most functions, once it's given to you as a formula, the answer would just be it's continuous on this domain, and whatever values you have to exclude from the domain is not continuous, of course, and then just investigate the limit to see what type. That's all it is. The only exception to this rule is samples like number 3, piecewise functions, which is not just the domain, because because piecewise there could be a gap, right? Functions made out of one formula, they don't have gaps. They could have holes, infinity, asymptotes, but there are no gaps, there are no pieces, unless there is an absolute value. Remember, absolute value looks like a formula, but it's not, it's piecewise. Yes? But other than that, they have no gaps. The gaps may show up in these cases. So you have to take that into consideration. We're going to see how to do that in number 2. Okay? But if it's just one full formula, like 1 or 2, it's just a domain question, really. Okay. Let's look at number 2. So number 2 is g of x equals x squared minus 1 over x minus 1. First thing that we do is domain, right? Let's find the domain. What's the domain of this function? All real numbers except 1. Everybody okay with this? So the domain is all real numbers such that x is different than 1. So negative infinity to 1, parenthesis, union 1 to infinity. Just by looking at it, if you are taking, you can just now do this by inspection. If you take any limit at a point other than 1, would that limit exist? Remember, 1 is the one that will give you 0 down here, okay? If you are approaching a number that's not 1, Will this limit exist? Yes, it will be whatever the top is divided by whatever the bottom is, right? So it will be equal to the value of the function. In other words, this function is continuous on these two intervals, right? The only problem is one. Now just write here a little sentence. I'm going to tell you a theorem later that says that all these functions are continuous on their domain. So you don't, after we know that, then you don't have to write the sentence that I'm writing anymore. But because I haven't said that, I have to write it. So if a is different than 1, then it's clear that the limit as x approaches a of the function equals the value of the function. So in other words, g of x is continuous on all real numbers except 1. Okay? And moreover, g of x is not continuous at x equals 1. Now our job is to say the type, right? So we know that it has a discontinuity, namely at x equals 1. What type of discontinuity is this? What do we need to do to figure this out? We have to take the limit, right? So we take the limit as x approaches 1 of the function. And then we see what happens, okay? So this is limit as x approaches 1 of x squared minus 1 over x minus 1. What's going on here? This is a 0 over 0 situation, right? So what do? So one of the techniques is we have to do something, right? So what's one of the techniques? Factor and simplify if possible. What's the answer? 2. So the limit equals 2. Right? So what type of discontinuity do we have? What is it? What word come to your mind? Removable. You remove the discontinuity, right? You take it away. So it's a removable discontinuity. Remember, the limit exists. Okay? Because the limit exists, then the discontinuity is not too bad. It's removable. So at x equals 1, we have a removable, or let's say G has, not we, G. G of x has a removable discontinuity. Did you understand this?
X equals 1, right? Oh, yeah.
Yes. Are we okay? All right, because it's removable, this can be fixed. So let's fix it. So give me a function that's the same as a function g, but with this problem fixed. And when I say the same, is almost everywhere. In other words, okay, to be different at one point. Okay? Let's see. Graphically, how does the function g looks like because of this? Notice that this simplification we could have done it all the time, right? So, as we have mentioned before, the function g will be the same as the function x plus 1, except that x plus 1 is okay at 1, g is not. So what is the graph of g? It's just the line x plus 1 with a hole at the point 1, 2. That's all it is. It's a line x plus 1, but it has a hole. Do you understand this? So how do we fix the function g? So fixing the discontinuity, in other words, removing the discontinuity, right? We say it's removable. Okay, let's remove it. So removing the discontinuity or fixing the discontinuity, well, I'm going to define a new function. I'm going to call it capital G. And what will be this function? I'm going to make it piecewise. So it's going to be my function g. So it's going to be x squared minus 1 over x minus 1, as long as x is not 1. So if x is different than 1, the new function is the same as the old function. Okay? Now, when x is equal to 1, remember, to fix the discontinuity means we want to make sure that we get something continuous, right? So what number should I put here now? 2. So now if you look at this function, it's continuous everywhere, right? At a point different than 1, you should be looking at this formula, and as you know, away from 1, this is a fine formula for continuity, right? As we saw above. Now when x is 1, the value of the function is 2, but when you take the limit, what happens? When you approach 1, you're doing it from the right or from the left, but the x itself is not 1. You understand this? You're getting close to 1, but it's not equal to 1, so you should be looking at the formula anyways. And as you know, the limit is 2, so it matches the value of the function. Yes?
So making it into a piecewise function is the only way to fix it, right? Is that
Yeah, so because all you have to say is, okay, we know the limit exists, just make sure that the value of the limit is the same as the value of the function. Because our function doesn't have a value, the value 2 when x is 1, in fact, it's not even defined, we just force it to be 2 by doing this. If it was piecewise, but this had a 3, it wouldn't be continuous, right? Then just change the 3 for a 2. Remember, just change it at one point, that's all you can do to fix it. And you can always do that if the limit exists. Okay? So even if it's not piecewise, you make it piecewise like this to make sure that it's continuous. That's how you fix it. What we just did here was go and fill in the dot. So we said here, oh, if you want to fix this picture, all you have to do is come here and do this. That's what we just did. By making it piecewise and saying, 1 is 2. We went there and we fill in that dot. Okay? All right. Questions? So the summary is that function is continuous from negative infinity to 1, union 1 to infinity, and then a 1 is not continuous, but this continuity is removable. That's analysis. Now, you could be asked, okay, fix it. Well, this is how you fix it. Okay, let's make it piecewise and then redefine the function at the point and define it to whatever value it needs to be continuous. So make it match whatever the limit is. Okay, that's what you do. All right. So for this type of questions, it's different than solve an equation, solve this, solve that. You need to know what you're doing. You need to understand the definition. Otherwise, you don't know what to look at. You don't know what to analyze. Why it's important to understand the definition. Okay. So it would be easy if you know what you're doing, if you understand the definition. If not, then you're just staring at the function and you have no idea where to start. Okay. All right. So let's take a look at this one. Okay, so we want to analyze continuity for this function in general. So that means that we need to analyze what happens to this function over all real numbers. So let's see. First, I guess, let's not lose focus on this. So let's ask for the domain of this function. Who can tell me what's the domain? Very good. For piecewise functions, the domain is right there in front of you. Domain is right here. When it's less than or equal to 0, use this formula. And if this is a well-defined function, this formula better work for all these numbers. Okay? For example, if this had an over x plus 3, then this wouldn't be a well-defined function because negative 3 is here, but then I cannot use that formula. So what are we doing? Okay? So when you define something piecewise, if this is well-defined, that means that your domain is explicitly written here for you. So this is saying, if it's less than or equal to 0, use this, so you are okay. If it's bigger than 0, use this. So you can plug in whatever you want, right? Because any number is either in the first piece or in the second piece, any value for x. Yes? So domain is all real numbers. So here the domain didn't really gave us any useful information. Well, yes, it gave us something. The function is defined everywhere. Okay? So if it's not going to be continuous, it's because there is somewhere in which the limit does not exist, or the limit is not equal to the value of the function. Right? But we have a value. Okay, so what else do we do now? Because every real number is fine here. So what do? Well, point is that because this is piecewise, there are 3 cases to analyze, naturally. Less than 0, bigger than 0, and then what happens at 0 itself. Do you understand this? So, first piece, second piece, and then that point at which the function is changing pieces. Because there could be a gap there. That's something that has to be analyzed, right? So 3 cases to consider. And if you have more pieces, then there will be more cases. Do you understand this? each of the pieces, and then all of those points at which you have changed your formula, you have to analyze those individually. And when you are analyzing a point, it's just condition 1, 2, and 3. Make sure that they check out. Okay, to look at continuity. So 3 cases here, 3 main cases. So that would be x less than 0 and x bigger than 0, and then x equals 0. Do you understand this? So let's look at the first case. So x less than 0. So in other words, this means negative infinity to 0. Okay, as that interval. So that's an open interval. We just have to analyze continuity of this interval. Remember, that means the function has to be continuous at every single point here. Okay. Well, in this case, what is our function? What's the formula for the function in this case?
X plus.
This is just x plus 1. We don't have to worry about the second piece, because when x is less than 0, that's what we're looking at anyways. What type of graph is this? There's a line, so there's nothing wrong with a line, right? And if you think about it, it's defined, the limit is going to exist, and it will be equal to whatever your x is plus 1. Yes? So this is certainly continuous. There is nothing going on here. So let's go to the other piece. X bigger than 0, that means from 0 to infinity, right? What's the formula for our function in this case? As e to the x. And what do you know about e to the x? Think about the graph. How does the graph look like? It's a very nice graph, right? It's exponential. It has no gaps, nothing wrong with it. So it's going to be defined. You can always plug in. If you take the limit, what will be the answer? As x approaches a number, what will be the limit? E to whatever that number is, right? You just plug in. So the limit will match the value of the function. So no issues here. Continues. Remember, once you have a single formula, it's just the domain. And the domain of e to the x is everything. In particular, from 0 to infinity is fine. Okay? So no issues in those 2 cases. Now, what happens at 0? Here there could be an issue, there may not be an issue. Because we may be in the presence of a gap or not. So, because this is a point, now we need to go through the 3 conditions. So condition number 1, the value of the function. Does it exist? Yes or no? So you figure that out by just plugging in h of 0. Can we find this value? What's the value of the function at 0? 1. Yes? And what piece do you need to plug in at? The first one, right? So it's 0 plus 1, which is 1. So condition number 1 is a go. We're good. But remember, that's not enough. We need to go and look at the second condition. What's the second condition? So does the limit exist? So limit as x approaches 0 of h of x. So the question is, does this limit exist? How do we compute this limit?
By plugging in 0 into x.
So remember, first you need to know what is h. You plug in once you know what's h, once you know the formula. So what's the formula for h? When x approaches 0.
X plus
4. Why? Why not e to the x?
equal to.
Do we care what happens at 0? In the limit? Do we care what happens at the point? No. So what do we need to do? We have to look at side limits. The only way for you to understand, to see what formula h is by approaching 0 from the sides. If you are to the left, it's x plus 1. If you are to the right, it's e to the x. Remember, when you have piecewise and you're taking the limit at that point in which the function changes formula, you're forced to look at side limits. You don't have side limits. How do you know what formula to use? Do you understand this? Yes? Now we're putting together all the little things that we have been discussing, okay, in these past 2 weeks. Okay, so for this we need side limits. So need side limits. All right, so we're gonna do the limit as x approaches 0 from the left, and then we're gonna do the limit as x approaches 0 from the right. Okay, so here the point is that when we do this, this allows to say that, okay, this means that x is less than 0, right? Because we are approaching 0 from the left. So now that we know that x is less than 0, we know what piece to use. What piece do we use? The first one, right? X plus 1. So that means that we are really looking at x plus 1. And what is its limit? 1. Okay, so that limit exists, okay? Now, let's go to the right limit and repeat. What do we know about x here? This means x is greater than 0. So that means that we should be using second formula, right? So that will be the limit as x approaches 0 from the right of the function e to the x. And what is this limit? Well, that's e to the 0, which is 1. So what's going on here? Do the limits match?
Yes.
So they're the same. So what can we say to number 2? Is the answer yes or no? And the answer here is a big yes, right? Are we done?
No.
We need to make sure. What do we need to make sure now? Well, that's what it means when we say yes, that the side limits match.
Oh, no, that.
And now we need to make sure what? 1 and 2 give you the same number, right? The limit has to be the same as the value of the function. So, is it? So let's see, the answer is yes. And what's the limit? The limit is 1. Because remember, when the side limits match, that means the actual limit exists and equals whatever that number is with side limits. So all we have to do now is compare the number in 1 and 2, and indeed they're both 1, right? So the answer is, so for number 3, now here we don't need to compute anything because we have everything. So the limit as x approaches 0 of h of x is equal to 1, which is the same as the value of the function, let's see. Do you understand this? Yes? Okay, good. So then what does that mean? So there's a check mark as well. So number 1, 2, and 3 were satisfied. So what's the conclusion? Is it continuous at that point? So h of x is continuous at x equals 0. So putting everything together, it's continuous for less than 0. It's continuous for greater than 0. And we saw also that it's continuous at x equals 0. So that means our function is continuous everywhere, right? So h of x is continuous everywhere. What I mean, what we mean by this is from negative infinity to positive infinity. Okay. All right. Questions? For example, if I would have done here this, what do you think would have happened? If we had e to the x plus 1,
Yeah, they wouldn't match.
the side limits, there will be a problem at the side limits, right? What would be the limit from the right in that case? 2. It will be 2. So then we will have a gap because the side limits are different. So our function will have a gap. So it will be a non-removable discontinuity. You understand this? So, for example, a typical problem would be, let's say that I would have done this, or maybe this plus a, whatever. Just put an unknown in there and then ask you, okay, figure out what a needs to be so that this function is continuous everywhere. Okay, so how would you approach something like this? You do exactly the same thing. So less than 0 is a line continuous. Greater than 0 is an exponential plus a number, still continuous. Yes? So at 0, what happens? Is defined? Yes. The limit? Okay, let's see. To the left, the limit is 1. To the right, what will be the limit? 1 plus a. Right? Now, we want the function to be continuous. So now here, what do we need to require? Left and right, they have to be the same. So 1 equals 1 plus a. 1 must a be 0. So if you want this to be continuous, a better be 0. Do you understand? We're going to do another example later. But that's the idea. You have a bunch of problems like this in the home. Okay? They give you a piecewise function and there's an unknown in there, a constant, and then your job is to find what that constant has to be so that the function is continuous everywhere. Okay? And typically, the limit step is the one that tells you what's going to happen. Okay? Because you have to match the limits. Or if the limits are okay, then the last step may be the one when you match the limit and the value. You have a little equation and you solve for the unknown. Okay? Okay. So that's number 3. And then for the last one, sine of x. What do you think? What's the domain? What's the domain?
Or real numbers.
Or real numbers, right? You can plug in whatever you want. Remember the sine function is, periodic function. It keeps going all the way to the right, to the left, non-stop, right? It's trapped between 1 and -1. That's the range. But the domain is all real numbers. Okay, so we don't have any candidates here for discontinuity. Do we foresee any problem with this function? I mean, before it was piecewise. It was all real numbers, but it was piecewise. So we had a reason to at least investigate further, right? Now here, this is not even piecewise. The same function. So any value that you pick, any number that you pick, can you take the limit? And what would be the value?
The limit itself.
Okay, and what would that be? Let's see, x approaches 20. What's the value of the limit? Sine of 20. So the value would be the value of the function at that point. Yes? In other words, it's continuous. Okay, remember, once it's given to you as a single formula, it's continuous on its domain. The domain is of real numbers, as the function is continuous everywhere. Okay? And it's continuous everywhere. That means negative infinity to positive infinity. Are you okay with this? Okay, so I guess it's time to tell you. Okay, so let me give you the definition and then I'm gonna tell you the properties. The point is that the same way that we have properties for limits, we have it for continuities. You can now mix functions. Remember, the limit of the sum is the sum of the limits, right? What do you think is going to happen if you have two functions that are continuous at a point? What happens if we add the two functions? What's going to happen at that point? Would you lose continuity if you add the two functions? Well, they both are defined because they are continuous individually, yes? So the value of the sum is the sum of the values. Do you understand this? The limit. Will the limit exist? Well, there is continuous, so this limit exists, and as you know, the limit of the sum is the sum of the limits. So the limit will exist. And moreover, by continuity of each of the functions, this limit is whatever this value is, this limit is whatever the value of this function is, so the limit of the sum will be equal to the value of the sum. Okay? Moral of the story. If you add two continuous functions, you still have a continuous function. So the sum of continuous function is continuous. The difference of continuous function is continuous, the product, the quotient, unless the bottom function is 0, and all of that business. Okay? All of those basic properties that we have for limits, they apply for continuity. And also composition of continuous functions is continuous. This allows to say that things like sine of 2x, for example, is continuous. Okay? And therefore, sine of 2x over x squared plus 1 is also continuous. Why? Even though you see a fraction here and you may say, well, there could be an issue. Well, no, because x squared plus 1 is never 0. Right? This is always possible. Therefore, there's no issue with this formula. The domain is all real numbers and it's going to be continuous. Because the top is continuous, it's a composition of two continuous functions. The bottom is continuous, it's a polynomial. It's the sum of two continuous functions. And the R function is a quotient of two continuous. So it's continuous. So these properties that I'm mentioning that I will write soon, they allow you to look at a formula like this and say it continues. And move on with your life. And you don't have to write anything. I mean, if you want, you can write, but it's basically this justification that's said. Okay? So continuity is basically look at the domain. Unless it's piecewise, and then there are some points that you have to then force to look at conditions 1, 2, and 3. Remember, conditions 1, 2, and 3 are only for a point. Okay. So, but before I write those, let me give you the definition of continuity on a closed interval. So, definition. This is continuity on a closed interval. So a function y equal f of x is continuous on the closed interval AB. So remember, closed interval means that it's everything inside the interval AB, but also you include the endpoints, all the numbers between A and B, but also you need to include A and you need to include B. Okay, so it's continuous in the closed interval AB if, let's see, number one, if f is continuous on the open. We already know what this means, so it has to be continuous at every point inside the interval AB. But now we need to say something about A and we need to say something about B. The point is that when we say I want to analyze the function on this closed interval, I'm telling you I only care what happens to the right of A. I don't care what happens to the left. And I only care what happens to the left of B. I don't care what happens to the right of B. Otherwise, I wouldn't have specified the interval. Okay? So at A, we only are interested in right continuity, which is the same definition that we have above at a point, but you look at a right limit instead. And at B, we only care about left continuity. So f is continuous on the open. 2, f is right continuous at x equals a. And let me spell this out. So it has to be defined. The right limit only exists and those two numbers, they have to match. Okay, so the word right continuity is because you're taking a right limit. That's why we call it right continuity. Okay, and it's right because it's from A to B, so you're only interested to the right of A. And then number 3, it has to be left continuous at B. Number 3, f is left continuous at x equal b. And you understand what left continuous is, right? It's the same definition as above, but instead of a right, you write a left limit. Just change the plus with a minus. It should be clear what it is. So this is defined similarly for in a similar way to number 2. Okay. Okay. Are you okay with this? I mean, this is just a little detail, but you need to know that if you're looking at a closed interval, when you look at the limit at one of the endpoints, you don't have to look at the full limit, you only look at the corresponding side limit. Okay? If it's the left endpoint, you need to look at the right limit. If it's the right endpoint, you need to look at the left limit. Okay? Remember, you draw a picture, it will be clear. You only care what happens to the right of A, and you only care what happens to the left of B. Okay? That's basically what it is. Outside of this interval, you're not interested in what's going on. You only want to know what happens here. Okay, so I guess little example. Discuss continuity of the function f of x equals square root of 1 minus x squared. What's going on here? What's the domain? Should we include the endpoints? Or not? What's wrong with you can plug in and get 0. Remember, domain is what is it that you're allowed to plug in. I'm going to explain how to find the domain of this, okay? In case some of you may not remember. So again, remember, domain is just have to figure out what are the good values for x. So what you're allowed to plug into this function. You have to look at the formula and say what could go wrong, right? What can go wrong here? Having a negative inside the square root. You see a square root, the red flag is the stuff inside cannot be negative, right? Same way that you see a fraction, the red flag is the bottom cannot be 0. So here, the stuff inside cannot be negative, so you want to make sure that whatever is inside is greater than or equal to 0. So that's the first question, the first thing that you need to figure out. So for the domain, you need to say, okay, the stuff inside the square root, I better have it greater than or equal to 0, because otherwise we have an issue. So we're going to solve this now, but is there any other issue? Let's say that we already cleared this up. Is there anything else that we need to concern ourselves with? I mean, you have to look at the formula inside. The formula inside is a 1 minus x squared. There's nothing wrong with that, right? You can plug in whatever you want in there, you square it, and then do 1 minus that. It's not a problem. The problem is that could give you something negative, and then the square root complains, but we're solving that here, okay? So this is the only thing that we need to analyze. So now, question, how do we do this? This is what we call a nonlinear inequality. How do we solve nonlinear inequalities? It's nonlinear because of the square. If you have this, exists, right? Just move the x around and then you get x less than or equal than -1, right? But we cannot do that here because this is nonlinear. So how do we do it? Do you remember this? Okay, you mean multiplying by -1? Okay, you could, but you don't have to. So I guess my question to you is, if you have a function and you want to analyze this question, and this function is not a linear function, so this function is not of the form mx plus b. It's not a line, okay? It's a non-linear function. How do you do this problem? For any function, could be a fraction, a rational function, a log, an exponential, whatever. How do you answer this question? Okay, and then what?
Then you square root both sides.
It doesn't have to have square roots. So for example, what if this was like this? What do you do?
You multiply x plus 3 on both sides.
Yeah, but you have a 0, so then you will be ignoring the x plus 3, really. So what do you do in these cases? So remember, this is called a nonlinear inequality. The way you deal with nonlinear inequality is the following. First, you need to find the zeros of the function. Whatever makes the function equal to 0. And now you will understand it better because you know continuity. So if you know all the values at which the function equals 0, what does that mean? Let's say that we find the zeros. Let me return to the original case. As you know, this function is going to have two zeros, right? 1 and -1. So here is -1, here is 1. Yes? Yeah. Now, these are the only zeros that this function has. Now, because this function itself, 1 minus x squared, is continuous everywhere, right? There's no problem with this function as it is. It's continuous everywhere. When you sketch the function, it is only allowed to cross the x-axis at 2 points, at -1 and at 1. And this is true for any continuous function. When you draw the picture, it will only touch the x-axis at the points at which the function equals 0. Touch or cross, okay? All right. Then that means that to the left of -1, the function is either all the time above the x-axis or all the time below the x-axis. In this case, it comes out as below, right? Because it's a parabola that opens down. But because the function is continuous, that means that to the left of -1 is either above or below. I'm going to tell you how you can figure that out pretty soon. Then you cross. Then between -1 and 1, it has to be on one side of the x-axis. It cannot change from top to bottom because if it changes by continuity, it has to go through the x-axis. You cannot jump. You cannot have a hole. But then it will create another 0, and we don't have any other 0, right? These are the only two zeros. So it has to be up here, and then it will remain below. Yes? Now, here I'm using the fact that we know the function, but if the function is continuous, we know once you put the zeros, the line is split into 3 intervals, and in each interval, the point is that the function always has the same sign. It's either always positive or always negative. And how do you detect that? Pick a point, plug it in. Whatever sign sign you get for the function, that's a sign on the entire interval. That's how you solve nonlinear inequalities. Now, what if the function is a rational function? So there are values that is undefined. So in this step, in this set of numbers, it will include the zeros and the values that make the function undefined. So if it was like this, now I will change story. We will have -1, we will have 1, and then I will also have -3 in here, which, as you know, will be a vertical asymptote, right? But still, the pieces still continuity. So once again, on each piece, now there will be 1, 2, 3, 4 pieces in the x-axis. On each piece, there's no other issues, so the function is continuous on each of those pieces, and therefore it's either all the time above or all the time below. Why? Because if it was above here and then it all of a sudden becomes below, you will have to go to the x-axis by continuity, giving you another 0, but we only have 2 zeros, and they are already there. If we had another one, it would be here in our list. Yes? So steps: find the zeros, find the value that make it undefined. Once you have those values, what do? Put them in a line, all the numbers. The lines split into a bunch of pieces, and then you start picking points and plugging. For example, if this was the problem, I'm doing it like this so I just see the whole picture, not just with this one that's easy. So just start plugging in. For example, here, I will pick -4. If you plug in -4, what do we get? Negative on top, and then a negative in the bottom. Negative divided by negative is positive. So that function is positive here. Okay? Pick a point here and repeat. Say -2. You put it here, what do you get? Negative. You put it here, you get positive. Positive divided by negative is a negative. I'm going to pick here 0, positive on top, positive in the bottom. So that's a positive. And then on the other one, I'm going to pick a 2. So negative on top, positive in the bottom. So that's a negative. What this is telling me is where the function is above or below the x-axis. In this case, what do you want? To be above or below? Well, we are asking greater than 0, so you want above. So everything that has a plus is your answer. It would be this and this. And that would be your answer. That's how you solve nonlinear inequalities. You did this in pre-calc for polynomials and rationals. Now I'm telling you, you can do this for any function. It doesn't have to be polynomials and rationals. If you have an exponential, you have a logarithm, it's the same idea. You need to find zeros, and you need to find the values that make them undefined. Put them in a line and play this game. Okay? Now, the original question that we had was this one. Still, we need to do the same process, but it's now easier because we don't have the denominator that I was explaining below. Okay? So we need to find the zeros, and as you know, it's easier if we factor. So I'm going to go ahead and factor. And so we know we need to find the zeros, and certainly the zeros are -1 and +1. Yes? So we put them in a line. And then, let's see, should we include the zeros? Well, we want to be greater than or equal to 0, so yes, we should include the zeros. If it was greater than 0, then we don't include it and we do open circles. Okay? The line is split into 3 intervals. So now just pick points and investigate. So -2. So I plug in -2 here, and then I get a negative over here and a positive over here. Negative times positive is a negative. You pick 0, you plug it in, you're going to get positive times positive. And then if you pick 2, or whatever is your favorite number of this interval, okay, you're going to get positive here, negative here. So that product is a negative. Because we are looking at greater than 0, then we only consider the plus, right? If you wanted to know when this is less than 0, then the answer would be negative infinity to -1 union 1 to infinity. Whatever you see the minus. Do you understand this? Okay. So this is the domain. So domain is -1 to 1 with square brackets. And that means the function is not even defined outside of this, so we don't need to consider what happens to the left or to the right, to the left of -1 or to the right of 1. But now there's a closed interval, and to analyze continuity here, we have to use the definition above, right? So on the open, so for continuity, we first have to analyze what happens on the open interval, okay? And certainly the function square root of 1 minus x squared, if you were to take the limit of this, you just plug in, right? And there wouldn't be any issues. Do you understand this? If I take the limit as x what do? Just go and plug in, and you get your answer. And that's true for any value in here. So here this is continuous. And later it will be further justified because it's a composition of two continuous functions. 1 minus x squared is continuous, and the square root function is continuous. The composition is continuous. So as first one, then the second, the other condition that we need to look at is right continuity and -1. Okay, I don't know if I should wake him up. Well, that's an interesting background to have. So, style. Okay, so first, value of the function. What's the value of the function at -1? 0. It's pretty good. Second, limit as x approaches -1. What limit do I need to consider here? Look at the picture. What side are we to -1? To the right. Right? So this is the left hand point, so would you look at the right limit? It's right continuous. So from the right. Okay, that's really annoying. Okay, so if you're tired, you can excuse yourself out and then, I don't know, put water in your face or something. But you are snoring, and that's not a good background to have. Are you okay? Just excuse yourself. It's fine, and it's fine. It's better if you're gonna be here. You need to be awake. Otherwise, don't be here. There's no point if you're not awake. I mean, I already know these. I'll make sure that you know it. So, okay. What's the limit? So, this is square root of 1 minus x squared. What is this limit? 0. You just plug in, right? I mean, you always plug in. If you get in trouble, that's when you say, okay, what do I need to do? In this case, nothing to worry about. And notice that the values are the same, right? So limit as x approaches -1 from the right equals 0, which is actually the value of the function. Are you okay with this? So we have right continuity. So f is right continuous at -1. And hopefully you see that similarly it's going to be left continuous at 1, right? There's no need for me to repeat the same thing. To check right continuity, to do left continuity at 1, you do exactly the same thing, but you look at left limits. But the same thing is going to happen. Similarly, f is left continuous at 1. So overall, f is continuous on the full closed interval. Are you okay? So on Wednesday, I'm going to give you the properties, and then we're going to do more examples and more interesting ones. But just to close this, can you tell me how this function looks like?
It's like an exponential.
Okay, good. What is that?
I don't know how to describe that.
Is that the square root function reflected over the x on both sides?
It will be, I mean, you have 1 minus x, but you don't have 1 minus x. So it's 1 minus x squared. If we call this y, let's do it here. If we call this y, right? I can square both sides, then move the x over. Now, I want you to remember that our original y is greater than or equal than c, okay? Because that's our y, the square root. But we can play with that and we get this. What's this equation? This is a unit circle. So what we have over there is just the top half of the circle. That's half a circle. So the graph of that function is This one. It's half a circle. If you want the other half, you have to put a minus. Minus negative square root of 1 minus x squared, that's the lower half of the unit circle. And the same way, if you have the square root of 36 minus x squared, what is this? This is the upper half of the circle with center at the origin and radius 6. Yes? And so on. We're going to need this later, right? When we talk about integration and so on. All right, so see you guys on Wednesday.